I was saying, well, this was a reduced G, right? When it's put into this formula over here, right, you can see we don't have any 4 pi in our force, you know, our gravitational thing there, right? So this reduced G already has 4 pi divided into it. That's why I call it the reduced G, because it's reduced. We've divided a 4 pi into it, right? This G, and we never notice we never use that line, but that line is there. But if we use the real G, this is what we'd have to have. We'd have to have G over 4 pi, right? Because G over 4 pi equals this, right? Because the reduced G is smaller, so it has to be multiplied by 4 pi to get the bigger, you know, real G, right? So anyways, I was saying that you would have to have a formula like this, because this G, you know, it's not having the 4 pi. So I was thinking you put the 4 pi there. That's not right, okay? I want you to let's take this formula from here, right? And put it down here, okay? Now I want you to think, right? If this was the reduced G, right? What do you replace it by? You replace it by a G, regular G over 4 pi. So that's what I did. Here's regular G over 4 pi. Now look at the formula, okay? 4 pi r. That's the circumference, right? That's the circumference, right? A cycle, a wave, a rotation, a sine, a circle. It's basically the circumference of the Earth. But you can see when you put that 4 pi in there, the 2 over 4 comes out to 1 over 2. The 1 goes away, because, you know, why would you leave it in there? So you end up with a 2 pi r. And this formula here equals c squared. And what does c squared equal? It equals 1 over e naught mu naught. Permittivity, permeability of the space. So this is where the 2, remember I kept saying, where is that 2? How does that 2 come into play? Why is there a 2 in this formula at all? Okay. Why? Because they're using the reduced G, okay, and there's a 4 pi underneath here that you don't see when you use the reduced G, because it's reduced. It's already had the 4 pi divided into it. But this is what it really looks like, right? And the 2 goes away. The 2 isn't nothing. It's the 4 pi is something. It's 2, you know what I mean? It gets reduced to 2 pi, because 2 times r is diameter. And diameter times the pi is the circumference. See, this is the formula with the, you know, if you use the regular G, you have the, you know what I mean? If you use the reduced G, you can see how it's different. The pi is taken out, right? Because the 4 pi would be reduced to 2 pi, you know what I mean? But now you see, if you rearrange it for the mass, right, like up here, right, okay, and you change this reduced G that they're using, right, to a regular G, this is what you get, right? And then that goes down to this, right, 2 pi r times c squared divided by G. But that actually goes down to here. Its mass, or kilograms, equals 2 pi r, the circumference, divided by big G, permittivity and permeability of space-time. This is the actual formula, right? See, when you have this 2, right, and you have it over 4 pi, it equals 2 pi. So now let's go on to my thingy. We're going to plug my mass into this formula, right, with this Schwarzschild radius, and we will see what my Planck length is, okay? Apparently it's going to be an infinity or something. Something's going to go weird, right? Because nothing can be smaller than this length. Right. Now I want you to look, another reason, you know, I can't really talk about this because I only have like 20 hours of calculus in, and I don't know calculus, they're doing calculus. But when it comes to that 2, remember how I was saying about the 2, right? And then I incorporated it so it was, you know, 2 pi r. But look at this, how, because they get this escape velocity in that from that 1/2 But they incorporate that 1/2 mass velocity squared that equals kinetic energy. And basically, you can see that they're having final and initial velocities. And when you do that, you get the difference and you divide it by 2 to get the average. That's where the 2 comes from, you know what I mean? Or the half. A half and 2, they're inverse to each other. And the another reason is because you got this 2a. When they're doing this, manipulating the equation around, they get this 2a. And that's where the 2 comes from, okay? I like my explanation better about the, it's 2 pi r as a circumference, but this is another, but I can't really go into detail about it because they're using calculus, and I don't have enough knowledge to really talk about it. But I can see that they're using initial velocities, final velocities, initial, energies and final energies and stuff like that. They're trying to get the average of something, you know what I mean? And that's where that 2 comes in. Well, like I said, we got our, John Black Planck distance. All we do is divide it, right? Here it is right here. We divide it by c, right? And we get this. 0.36 blah 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 times 10 to the negative 85th seconds, right? And then I move the decimal point over, right? And I make this bigger, so I make this smaller. So it ends up being 3.653 times 10 to the negative 86th seconds. Okay. So does this mean that's the smallest time that can exist? No. It just means that this energy is the lowest energy that any sine wave can have, and this mass correlates to that same energy. And if you put either one of these, either the energy or the mass, in this small distance, then you will create a black hole, right? And if you have light travel across this distance, it takes this many seconds. That's all it's saying. It's not saying anything else. Just like over here, this is Planck's units only say one thing. It says this: you can't take a picture of crap smaller than this length. Okay, if you do, you'll make a black hole, so you can't see it. Okay, it doesn't mean physics breaks down there. It means your ability to see breaks down. Okay, not physics. Your ability to see breaks down. Okay, and this is the energy. If you have this much energy, or this, because these are the same thing, kilograms of energy, they're equivalent, right? And if you have either one of these and you shove them into this little space, you will create a black hole. And how long does it take light to travel across this distance? This right here. Okay, doesn't mean physics changed and that, there's kind of magic going on. No magic, no magic. Just correlates to something. This correlates to us. We can't see below that because we can't take a picture. This correlates to the smallest sine wave energy that you can have. Like the mass just correlates, to being equivalent to this energy that is talking about a photon, right? And etc., etc. So here's all the equations, okay, that we use to get energy, mass, length, and time. These on the left, those are their equations. These on this over here, these are my equations. Okay, they're the same equations, right? But so you get the same exact answer either way, right? And these are the answers you get. There's no infinities, nothing broke down, right? I just created a black hole at a smaller length than that, so on paper. So I'm going to go back to this escape velocity equation and try to explain it. Keep in mind, most of the explanations, pretty much all of them, are using calculus. So I'm not 100% sure if I'm going to do this right, so keep that in mind, okay? when they were figuring out this escape velocity, okay, they're thinking that when you hit that point where you're escaping, you're finally away from the gravity, okay, your potential energy from the gravity will be zero, right? Because you're not affected by the gravity anymore. And your kinetic energy, meaning your velocity, you're going 11 whatever thousand meters per second or whatever it is for escape velocity for Earth, right? But the gravity is doing the same exact thing. It's pulling space-time down at the same rate, right? So you're not really moving that fast, right? When you finally get escape, all that velocity was taken away by the gravity, right? So you have 0 and 0 when it comes to kinetic energy and potential energy once you get away from the planet far enough, right? So they're thinking when they would, because your kinetic energy and your potential energy adds up to a certain energy. And it stays that way no matter what, you know what I mean? Your final equals your initial, your kinetic energy and your potential energy. After, your kinetic energy and potential energy still add up to the same thing, right? If you have this rock, above the surface of the Earth, right, and say this is 2 units of potential energy. If you let go of the rock and it starts falling, you're going to lose the potential energy, but you're gaining kinetic energy. It's going to be equal, right? And same way as if you throw the rock upward, you're giving, you have 1 unit of energy here, but you throw the rock up higher, right? You're giving that rock kinetic energy to get it up to here, right? And now it has 2 units of potential energy when you stopped, right? Because that kinetic energy was turned into potential energy, right? It always stays the same, right? And basically that's what they're saying here, right? So your kinetic energy and your potential energy, right, for your initial stage is there. Your final stage is 0 minus 0 of your kinetic and potential energy, right? Because all that velocity is taken away by gravity, right? But in your potential energy, you don't feel that gravity once you escape, right? And your velocity is taken away. So it's 0 minus 0. So this has to be 0 minus 0, right? So basically they took the kinetic energy equation, 1/2 mv squared. They took the equation from this, force from gravity, right? And they just say this is the potential energy, your gravitational energy. This is the kinetic energy from moving, right? Mass times velocity squared, right? Why is there no r squared? Because this is force, right? This is force. They want energy, potential energy, and that's in joules, right? So force times distance, right, which is r, is energy, is a joule, is a Newton meter, right? This is Newton multiplied by a meter. Now you got Newton meter, which is joules, energy, right? So that's why they did that. There's no r squared because that would be force, and they're talking about energy over here, right? So we know it's 0, 0. So this minus this is going to be 0, right? Because your initial and your final is going to be equal, right? So they cross off the m's, right? You can see minus sign here, right? They just add this to both sides, so this goes away, right? And then on the other side over here, you got gm r over r. What happened to the little m's? They cancel out. Once you do this, you divide both sides by a little m, and the m's cancel out on both sides, right? Then you multiply both of these sides by 2. Now you got v squared equals this, right? And that's where your 2 comes into your equation, right? Now this is squared, so you square root it. So you can have your escape velocity be just not squared. But now you got to square root your equation, right? And this is how they came to the conclusion that this is the escape velocity. This is the gist of what they're trying to say. I'm going to do is sooner or later about the fine structure and the anomalous magnetic moment, right? They're about changing from a per cycle type of thing to a per rad type of thing. The anomalous magnetic moment, okay, if you multiply it by 2 pi, you get the fine structure. If you take the fine structure and you divide it by 2 pi, you get the anomalous magnetic moment. Yeah, they're the same exact thing. They're just just changing one from per cycle to per rad. That's it.